Hey guys, today we were talking about conditional probability. And so conditional probability, that's actually your third definition, is the probability that event B occurs given that event A has occurred. And so that's what that B with the line A means. It's the probability of B given that A has happened. In independent events, that's where the occurrence of one event doesn't affect the other. You can see the probability of A and B equals the probability of A times the probability of B. We're not worried about what happened with that first probability. But in dependent events, that's when the occurrence of one event does affect the other. So that's like drawing cards from a deck. If it wants to know the probability of drawing one red card and then another red card, well, if you've drawn that first red card and you haven't replaced it, then your next probability will be affected because you have less red cards and less total cards in the deck. So this first one says, a game machine claims that 1 in every 15 people win. What is the probability that you win twice in a row? Well, if 1 in every 15 people win, the probability isn't affected by one person winning. So the first time, you have a 1 in 15 chance. And then the next time, you have a 1 in 15 chance. So if we're multiplying those, that's a 1 in 225 chance of winning twice in a row. So then this one, we're talking about grapes in a bowl. So a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and randomly choose another grape. Find the probability that both grapes are green. So we want the probability of green and green. So the probability of the first one being green is 36 over the total grapes in the bowl. So 36 plus 14 is 50. And then since you ate that green grape, now there's only 35 green grapes. And there's only 49 total grapes in the bowl. So if we put that in our calculator, we get 18 out of 35, or approximately 0.514 if we're getting the decimal. All right. An auto repair company finds that 1 in 100 cars have had to be returned for the same problem. How many times can you bring your car to the company before the probability that you have to have your car repaired for the same problem at least once reaches 75%? Okay, so we want to know when we hit 75%. And so we're going to approach this kind of like we did in our previous lesson, where we want the opposite here, because we know the probability that it's coming back for the same problem is 1 in 100. So how many times can we bring the car in before the probability that it's returned for the same problem reaches 75? So what about the probability that it's not the same? Well, that would be 99 in 100 times. So then if we bring it in one time, we get a 99 out of 100 probability, and then the next time 99 out of 100 that it's something different, and the next time is 99 out of 100. How many times can we do that? So how many times can we multiply by 99 out of 100? And so since that's the opposite, the probability that it's not the same, we need that 100% minus. We want to know how many times we're multiplying that, so the x goes up there. So then we're subtracting 1 from both sides here, and we get negative 99 over 100 to the x power is negative 0.25. So then we can divide by negative 1 here. So we get 99 out of 100. So is 0.25. How many, to the x power. How many times until we get to 0.25 then? Okay, so to do that, we're going to need to take the log here. And so when we do that, we have the log of 0.25, base of 99 over 100 is equal to x. So use your change of base, type that in your calculator, and we get x is approximately 137.9 times, or about 138 times. So to go back and look at what it was asking, it says how many times can you bring your car to the company before the probability that you have to have your car repaired for the same problem at least once reaches 75%. So you would have to take your car in 138 times for that to happen. Okay, so using this table at the right, find the probability that a listed student attended camp. So we want to know out of all of the students how many attended camp. So the students that attended camp are 45, 94, and 81. So we have 220 out of, we need to add all the students that didn't attend to our total list, so out of 469. And then you want to see, can I reduce that? And that doesn't reduce, so that would be your final answer unless you wanted a decimal approximation. So then find the probability that a listed student in the 8 to 10 age group did not attend camp. So in the 8 to 10 age group, did not attend is 62 out of the total 469. That also does not reduce. Find the probability that a listed student was in the 11 to 13 age bracket. So we're adding everyone in the 11 to 13 age bracket. So 81 plus 70 is 151 out of 469. Again, doesn't reduce. Find the probability that a listed student did not attend the camp. Well, we could go back and add those together, or we could do 1 minus 220 out of 469. And we get 249 out of 469. Also does not reduce. Find the probability that a listed student in the 11 to 13 age bracket did not attend the camp. So, probability that a student in the 11 to 13 age bracket did not attend camp. So, we have 70 students in the 11 to 13 age bracket, but we only have 151 total that did not attend camp or that are in the 11 to 13 age bracket. So then we can see 70 divided by 151 also doesn't reduce. So that's all we have on that one. Okay, so randomly select 2 cards from a standard deck. Find the probability that the first card is a diamond and the second card is red. So if we replace it is the first question that it's asking. So how many diamonds do we have in the deck? Well, there are 13. One suit has 13 cards out of 52 total cards. Then if we replace the diamond, half of our cards are red, or 26 out of 52 are red. So we get 1/8. That's actually equal to 0.125 without replacement. So we still have 13 out of 52 to choose from, but now we drew that diamond, and that's a red card. So now we only have 25 red cards, and we have 51 total red cards. So we get 25 out of 204, which is approximately 0.123. So we lowered the probability a little bit when we didn't replace that red card. Okay, in one town, 95% of students graduate from high school. A study showed that at age 25, 81% of graduates held full-time jobs, while only 63% of non-graduates held full-time jobs. Using a tree diagram, find the probability that a randomly selected student will have a full-time job at age 25. So, what we want to do here is we're going to kind of set up a tree diagram. So, graduated, did not graduate. The probability that a student graduated was 95%. So the probability that they didn't graduate then was 5%. So then of those students that graduated, 81% held a full-time job. So full-time, not full-time. So if 81% held a full-time job, that means 19% did not have a full-time job. And then of those that did not graduate, we have 63% that held a full-time job, which means that 37 did not have a full-time job. So now we want to trace this branch. We want to find the probability that a randomly selected student will have a full-time job. So we want to know full-time job, full-time job. So we have 95% of graduates, or 95% graduate, 81% of those have a full-time job. 5% do not graduate, and 63% have a full-time job. So 0.95 times 0.81 plus 0.05 times 0.63. So that's 0.7695 for this one, and 0.0315 for this one. So we get 0.801, or about 80% that held a full-time job of so randomly selected student, 80% held a full-time job. All right, guys, that's all I have for today. If you have questions, come in and see me. Otherwise, I will see you in class.